Spring from Imran's MacBook Air.
Hello, Tibra.
Hi, Imran. Sorry.
Okay, so I have two devices on.
Yeah. I Okay. Is that better now?
Yeah, it's perfect.
Okay. It's I don't know how to turn off the iPad sound. So, all right. So I'll probably won't have my video on. It's not something I do usually, but
Yeah, it's okay. We just need to ensure that you can share screen.
yeah, exactly. So um, I just wanted to try the new background I downloaded from Studio Ghibli. So how did Sajid's lecture go? How far?
Yeah, I think he has discussed the quantization and the excited states and
This is a reminder.
the
Water after every 4 hours.
sorry, it's a reminder.
This is a reminder. Water after every 4 hours.
Yeah, so this is a reminder. So he has discussed excited states like ground state of tachyon and then the excited state of graviton.
Very good. And he talked about the Virasoro constraints.
Yeah, that was in the first lecture. I think the lecture you attended, he discussed Virasoro algebra.
Okay. And okay, I'll review it. So that's fine.
Yeah, so just we won't wait too much because there are many participants who prefer to watch the recorded lecture.
Yeah, no problem. Yeah, I'm gonna just turn off my video then I can
Yes,
share.
please.
Or
Right.
let me
I
just
may
see.
also turn it off. So you can try sharing your screen.
Yeah, I am sharing my screen. Okay.
All right, so I
So
think you can begin.
all right. So welcome everyone. I am very excited to be here. Um, Last year, I visited Pakistan for a similar workshop, and it was a fantastic experience. It's too bad I couldn't be there in person this year, but this is the next best thing. Hopefully, we will continue this tradition, and we can keep,
Yes.
we can have it in person. All right. So before I begin, let me just introduce myself. My name is, sorry, I didn't want to write in red. My name is Tibro, but I write it in a way to confuse non-Bengali speakers, Tibra. So I am a faculty at BRAC University in Bangladesh. I'm also a founding member of a startup called Tensor. A higher education startup in Bangladesh. So these are my academic involvement. Like Sajid, I started off my life as an academic, as a string theorist, but I've moved around quite a bit. So right now I'm working on computational biology, quantum many-body systems, as well as I have one or two projects on string theory related stuff, but not probably pure string theory. So I have been tasked with the duty of telling you about string theory beyond perturbation theory, or more exotic and interesting stuff about string theory. So I'm going to just give you a very rough outline and ambition of what I want to do. I am not sure if I'll actually be able to do all of that, but we'll try to be ambitious. Okay, so actually I'm just going to switch my audio from the so just bear with me 1 second. So there's a slight echo that I want to eliminate. Okay, you should be able to hear me.
Yeah, this is better.
Okay, good. Awesome. Right, so I've switched to the iPad audio. All right, so what we're going to do is that I have a few topics in mind. And for today, I'm going to just talk about, a duality of string theory called T-duality, which is a perturbative duality, meaning that it appears in perturbation theory, but it gives rise to some objects which are very important in non-perturbative physics. And those objects are called D-branes. So the aim for my first lecture will be to start with T-duality and try to introduce the ideas of D-branes. Now, I'm not sure if I'll be able to finish that today. It doesn't matter. I want to go slowly and step by step rather than try to cover everything. So, and then I will talk about, okay, now that we'll have D-branes, how to describe the dynamics of D-branes. So we'll say something about the dynamics of D-branes. So, so basically I'll introduce the D-brane action or D-brane actions. I will also briefly discuss supersymmetry. I suspect Sajid has not talked about supersymmetry. Is that correct?
Yes, that is correct.
So I'll discuss the role of supersymmetry in string theory a bit informally, and how this leads to the various supersymmetric string theories, like the 5, different string theories. And the role that D-brane plays in them. Okay, so D-branes will play a prominent role. So, and then related to that, I don't know how much justice I can do it. I will talk about M theory. Now, M theory is the strong coupling limit of string theory. The strong coupling limit of string theory. It is not something that is so well understood. It is only formulated in certain regions of parameter space. There are some proposals for a non-perturbative formulation of M theory, but not much progress has happened. So then I'm going to switch gears and talk about holography which is in the string theory context is known as ADS-CFT. And in particular, I will discuss something called the Ryu-Takayanagi proposal. So this is a proposal for computing entanglement entropy in quantum field theory, entanglement entropy in CFT, conformal field theory, using a gravitational dual. Okay, so the comment I wanted to make is that this whole ADS-CFT, this business of ADS-CFT, this thing has taken on a life of its own. String theory has activity in pure string theory has eclipsed, has really gone down, but ADS-CFT is an extremely active field of research because it has been found to be a good probe for many aspects in theoretical physics, and it has had impact on, it has basically, has connection with gravity, condensed matter systems, quantum information. A lot of insight into black hole information paradox has come from ADS-CFT. So this is a tall order. This is to do all of this properly would take a 2-semester course, if not 1 semester, maybe 1 semester course at least, if not 2 semesters. So, but I have 4 lectures. So I'll have to cut some corners. I hope that's okay. All right, so I want to give you references. None of these things are my original work. And to be honest, right now I can only give you references about these 2. Okay, because I haven't written the other lecture notes. So I will give you references for that as I progress. So for this, I'm almost exclusively using the book by, I think it's Clifford Johnson, and it's called D-Branes. And it's a little bit older book, but not as old as Green, Schwartz, and Witten, which is also a very nice set of books. So just a word on references. My primary reference is going to be Clifford Johnson, D-Branes. I might also use a few other books. Polchinski is standard, but Polchinski is very hard to, it's a hard book to start from. Okay. So Polchinski, String Theory Volume 1 and 2. They're very good books, but they're hard. I find the old book by the 2-volume by Green and Schwartz and Witten to be very readable, but it's a bit outdated. I would say a bit. Still a great resource. In recent years, there is one of the better textbooks, in my opinion, is the string theory book by Blumenhagen. Lust and Theisen. So this is an update of an old book that Lust and Theisen wrote called Lectures on String Theory, and Blumenhagen has joined forces with them to write a very nice introduction. Okay, so so much for introductory stuff. I would like you to really interrupt me if you have any questions, and I don't guarantee that I will be able to give you any answers, but I will try. Okay. All right, so Sajid talked about the Nambu-Goto action for string theory, right? And then he said, well, it's a good start, but a better place is the Polyakov action. Now, one of you asked yesterday if there is an analog of sheets similar to strings. And the idea is there is. And the Nambu-Goto action is just a very simple action, right? It's just the determinant of the metric, square root of the determinant of the metric, right? That's the Nambu-Goto action, right? So where G is the induced metric, right? So of course you can write this for any dimensional spacetime. It doesn't have to be just for strings. So this is a two-dimensional integral, right? But it doesn't have to be, right? You can have, this could be an higher dimensional object, and you can write something, basically the area for a higher dimensional object, and that will give you the action for a higher dimensional brane. However, it's hard to write, if not impossible to write, a version of this action for higher dimension for the Polyakov action. In fact, the first person who considered quantization of higher dimensional objects, not just particles, was Dirac. So, and then similarly, Born and Infeld did something. Born and Infeld were trying to generalize electromagnetism in a way such that the self-energy problem of the electric charge would not be there. So they were inspired by special relativity, where there is a maximum velocity. So they said that, well, if we come up with a theory of electromagnetism where for weak electric field and magnetic field, it would just be Maxwell's equations, but for very strong electromagnetic fields, which is what happens when you come close to an electron, that it would actually, there would be some mechanism by which that field would be automatically regulated. So Born and Infeld worked on that. And in D-branes, this is now, the D-brane actions are now called DBI actions. So there are analogs of string actions for D-branes, okay? And hopefully we'll see that. This is just, addressing something that we saw yesterday. Okay, so string theory, one of the constraints that we saw in string theory is that if the Polyakov action, it has, what are the degrees of freedom in the Polyakov action? Well, there is the field the space-time field, which depends on the worldsheet coordinate, tau and sigma. And so this is basically, this is a space-time index which is sometimes called the target space index, because what are X mu's? These are maps from a two-dimensional worldsheet to some target space-time. And Sajid probably talked about what this target space-time should be for the bosonic string. That should be a 26-dimensional Minkowski space. Okay. So that is one of the degrees of freedom. The other degree of freedom is the metric on the worldsheet. As Sajid talked about, this is not the induced metric. This is not the pullback metric. This is a metric on the worldsheet. It is a non-dynamical degree of freedom because its equation of motion is algebraic. There's no derivative of G in the Polякov action, right? Because the Polякov action is something like this. And then we have this, sorry, I should use a different AB for, so this indices are the worldsheet indices. So we'll have this X of mu, del of B, X of nu, and let me make some space. So, and then these two indices are contracted by the space-time flat index, eta mu nu, and these two indices are contracted by the inverse of the worldsheet action. Right. And the worldsheet action is non-dynamical. And you might say, why is it non-dynamical? Why did not we say add a Einstein-Hilbert action as we do in GR, a two-dimensional Ricci scalar, and make this thing dynamical? And you can even have some boundary term, which we're not going to worry about. The answer to this question is that in two dimensions, the Einstein-Hilbert action, this is a topological density. Okay, and this thing is actually a topological invariant. This is the up to factors that I forget. This is the two-dimensional analog of the Gauss-Bonnet term. So by using this, we cannot introduce dynamics for G. Okay, so this goes away, right? So now, we saw that we had equations of motion for this thing, and when we gauge fixed, we got the same equation of motion as Nambu-Goto type, but we also get an equation of motion for this. What is that equation of motion? That is going to be S, according to the variational principle, we have to do this. Right. But this is the definition. So the equation of motion is this. But this is the definition up to some factor that I forget, maybe 2 pi or something. I forget this. This is what we called the energy momentum tensor. Okay. So the equation of motion for G is basically the vanishing of the energy momentum tensor. Okay. And now if you work out what are the non-trivial elements of the energy momentum tensor? In light cone coordinates, they are t plus plus and t minus minus. So what are plus plus? Sigma plus is essentially tau plus sigma. Sigma minus is tau minus sigma. At some point, we will basically do this, do something like this, and define a holomorphic coordinate and an anti-holomorphic coordinate, which will be something like this. Okay. Maybe, no, that's not correct. That's not correct. Okay, we'll cross that bridge when we get there. All right. So these are the non-vanishing part of the energy momentum tensor. Okay, so this is the energy momentum tensor. So the energy momentum tensor is important in GR, and it gives you it sources the gravitational interaction. So then these constraint then translates to this. Okay. So we shall see that these constraints, so this is classical. When we go and do quantum mechanics, imposing these equations as quantum equations lead to all kinds of inconsistencies. I won't go very much deep into those inconsistencies, but it's analogous to what we have in electromagnetism. Remember that in electromagnetism, we often choose the Lorentz gauge. And in the Lorentz gauge, we say this is equal to 0. But if I quantize it, if I quantize electromagnetism as a quantum field theory, so I promote this field to a quantum field, this is problematic. What we end up doing is that we take the positive energy frequency, and then we say that the physical states satisfy this. Right, this is known as the Gupta-Bloiler quantization, and it leads to a classical, it leads to this condition that in the physical, if you take the expectation value of this in the physical state, then that's 0. And this is seen as the classical quantum mechanical version of this equation. Similarly, just as this is too strong of a condition, this is also too strong of a condition when we do quantum mechanics. And this is related to the fact that there's gauge freedom associated with a mu, and there's gauge freedom associated with t's. What are they? The idea is that these energy momentum tensor, well, they are conserved, right? So, which is basically, you can derive that from the equation of motion. It's also the statement that your, sorry, I've switched to mu nu. I should use AB. There are statement that, there you have translation invariance and on the world sheet. So, so now if you then express this in these coordinate, what happens is something like this. Let me see. I want to make sure I don't want to write the wrong equation. So I just want to quickly have a look. The details are important. So yeah. So the idea is that this is 0. This is 0. So what you can do is that you can say, okay, I can define any charge. Suppose epsilon is some random function, say of sigma plus, sorry, sigma. And what you can see, well, what you can say is that, okay, if I then take some random function where I think I take this to be the case, then because this is not a function of sigma plus, this is also going to be 0. So roughly speaking, I'm being very sketchy here, this set of equations gives rise to an infinite number of conserved quantities. Okay. And so this is related to the fact that our two-dimensional surface, the string world sheet, our theory has diffeomorphism invariance. And the number of diffeomorphisms that we can do is infinite. And therefore, the group associated with the diffeomorphism invariance is an infinite dimensional group. And the algebra that we derive, called the Virasoro algebra, is essentially the Lie algebra of the diffeomorphism group. Okay. So did Sajid talk about the Virasoro algebra? Was the Virasoro algebra covered at all?
You mentioned the Virasoro generators at some point.
Okay, but maybe not the algebra, right? Okay, we'll discuss the Virasoro algebra then. Okay. All right, so I mean, all of this, I'm just making very formal, very informal comments. Now let's get a bit more technical. So we want to understand, what are the conditions what these things mean quantum mechanically. Okay. What do they mean quantum mechanically? So to do that, what we can do is that, well, these things live on the world sheet. So they're going to be periodic in the sigma direction, right? Sigma, if we have a closed string, we identify sigma with sigma plus 2 pi. This is the identification. And in the open strings, so this is for closed strings. And for open strings, sigma, I think, goes from pi to 0, something like this. Or Yeah. So now what we can say is that, okay, we can take the Fourier expansion of these things and define certain, the Fourier coefficients. So the Fourier coefficients for t plus t minus minus is given by t by 2, which is t is the tension. So this is the tension. Okay, which is related to the alpha prime. I think it's t is something 1 over alpha prime squared or something. So this is a string tension. And then what we do is that we take the integral. The Fourier transform is this. Okay, so this is the definition of Lm. What are going to become the Virasoro operators. So now, if I write this in terms of the mode expansion on the string, then one can write this as Lm is going to be sum over all the modes alpha minus m, alpha m minus n times alpha n mu mu. So from now on, what we'll do is that we'll just write this. So there's a space-time index, mu mu. We're just going to contract them and write them as a dot. So this is going to be our, in most cases, this is what we need, okay? So these are the expression for Lm. And how do you do Lm? Basically, you have an expression for T mu nu in terms of x's, right? Sorry, I should use AB. T mu TAB in terms of x's. Right. So, and these things, you have these expansions, right? Which I will give, but they have their own Fourier series expansion. So you just like plug them into this formula and do some integrations, and this is what you get, okay? So now one thing you can show is from the Polyakov action, you can work out the Lagrangian, and from the Lagrangian, you can work out what the Hamiltonian density is. So this is the Lagrangian density, and from there you can work out the Hamiltonian density is. And from the Hamiltonian density, what you can do is that you can then define the Hamiltonian. So if you do this, well, you go from here to here by doing the usual Legendre transformation. So if you work out what the Hamiltonian is, you find a surprise. And the surprise is that the Hamiltonian for the open string is the L0 mode, Fourier mode. Okay. It's this thing for m equals to 0. And on the other hand, the Hamiltonian for the closed string is L0 plus L0 bar. Okay. And so now, we wanted to ask what are these quantum mechanically, but we haven't gotten there. what we can say is that in terms of the Fourier modes, those conditions become this, right? So this is the condition, and this quantum mechanically, there's going to be some issues with that. Okay. Okay, I think it's a good place to stop and ask if there are any questions. Okay, I think there's the sigma condition for open string, as long as it is open, isn't it allowed to take any values from 0 to less than 2 pi? Yeah, it's I think you're talking about this, right? This is kind of a convention. Okay. So I think usually the convention is to consider one end of the string to be 0, the other end to be pi. Okay, any other questions? Okay, to give some flesh to these formulae, let me just rewrite something you should be familiar. So for the closed string, the target space coordinate can be written as say tau sigma, and this is going to have x mu by 2 plus x tilde mu by 2. And then we're going to have minus I square root of alpha prime 2, and then the 0th oscillator from the left part and the 0th oscillator from the right part. Okay. And there's going to be a term linear in tau, and then there's going to be another term, which is alpha prime by 2, alpha naught of mu minus alpha naught tilde of mu of tau. And then we have the oscillator terms. I alpha prime by 2, the sum over n, where n doesn't go, is not equal to 0. And then we have 1 over n, e minus 2in sigma. And then there's an alpha n of mu. And then we have I alpha prime by 2 divided with the sum over all the n's except 0, 1 over n, alpha n tilde of mu, e minus 2i. So here I'm going to put a plus here and sigma minus, okay? So this is the closed string expansion in terms of mode operators, okay? And there should be an I here, I think. Should there? Probably not, yeah. Are you familiar with this? I mean, I think Sajid was talking about this yesterday, right? Yeah. Okay, good. All right. So why am I flashing this formula? Because I want to kind of jog your memory about certain things. I want to jog your memory about the fact that, these guys have these are the center of mass kind of coordinates. And these are the zero modes. And these are the oscillator modes. Okay. So these are the oscillator modes of the ones that are going to create and annihilate states. So what I want to do is that I want to separate when writing L naught. When writing L naught, I want to separate the alpha naught and the alpha ends. So if I go here, so there, if I put m equals to 0, here there'll be m equals to 0. And then in this sum, there will be one term with n equals to 0. So I want to separate that from the rest of the bunch. So let's write that as half of alpha naught squared. And the rest of the bunch, there's a factor of half. But now I can just like pair up all the others. And we can write this as alpha n dot alpha n. So what have I done here? Let me go back and point out. So here we are saying this sum from minus infinity to plus infinity. So we are setting m equals to 0. And then for the value of n equals to 0, we are separating out that term. But now we have all the other terms from minus n equals to infinity plus equals to infinity. And here we have alpha of minus n, and here we have alpha of n. So you see that these are classical objects now. So we can commute them, right? We can commute them. So the tower from n equals to 1 to n equals to infinity, and the tower n from -1 to minus infinity, they're the same as long as we can commute these alphas. And because we are still doing classical physics, we can do that. So if I do that, then I can write an expression for L naught where it's just one summation and the factor of half here has gone away. So the other thing is that, remember that alpha naught is essentially the center of mass. The momentum, right? And therefore, if you go back and use the expression for the relationship between momentum and alpha naught, which let me remind you, alpha naught mu is alpha naught tilde of mu, and that was alpha prime by 2 square root p of mu. So if I use this, then my L0 becomes alpha prime p mu, or we could have just wrote p dot p, whatever you want to write, plus sum over these guys. Okay. But what is p mu p mu. This is the norm of the 4 momentum, but well, 26 momentum. So the 26 momentum, according to Einstein, is going to be equal to the mass squared. The minus sign comes from the fact that we are using a signature where the time part is negative, everything else is positive, right? So if I do this, then my L naught becomes minus alpha prime m squared plus sum over 1 to infinity alpha of minus n alpha n. So now if I look at the classical constraint, which is telling me L naught should be 0, that gives me an expression for the mass of the state. And the mass of the state is given by the string, the alpha prime, the string constant sets the scale, which is, what we expect, and this thing, right? So this is for the open string. For the closed string, we'll have two of these conditions, and therefore we are going to get just 1 second. Yeah. For the closed strings, we have L naught plus L naught bar, which is the Hamiltonian, and that has to vanish, and that's going to give us the mass of the states to be 2 by alpha prime. And now there will be contribution, oscillator contribution, both from the left moving part as well as the right moving parts. Okay. So these are the what we expect classically. And, anticipating quantization, this kind of makes sense because in quantization, this will have some sort of, a number operator interpretation, like in harmonic oscillator. And therefore, the occupation number of those different modes of harmonic oscillator are going to give rise to energy. And through the Einstein equivalence principle between energy and mass, they're going to contribute to the mass of the string. So the more, the more states that we excite, the more massive the string will be. Okay. However, quantum mechanically, we don't have a lot of faith in this equation. And the reason for that is that when we wrote those equations, we blissfully commuted these things. We commuted alpha n and alpha minus n. But when we quantize, those things will not commute. And not only that, if you start from, say, some normal ordering prescription and we quantize, we use the commutation relationship, the normal ordering constant that we will get is going to be infinite. And there's going to be problem with regularizations and stuff like that. Okay. So when we promote these things to quantum mechanical operators, the best, so when we promote these modes to, say, quantum operators, we have to take into account the ambiguity in the ordering. And therefore, we should have L naught is going to be something, the usual. So, and there is going to be a constant. And the value of this constant has to be, verified. It has to be derived using zeta function regularization and a few other, stuff. And in the end, the condition that the classical condition that we had, L equals to 0, we have to replace this. This is classical. Quantum mechanically, what we should do is that we should replace it as L naught minus A, where A is the constant which comes from this normal ordering business and all the other considerations, and that acting on a physical state gives us 0. Okay, this is what quantum mechanically, this is the most we can do. This is the condition that is not going to give rise to inconsistencies. Similarly, we'll have L naught, the right moving, will also give us 0. Okay. And because of this, constant, the normal ordering business, these L's will have a Lie algebra. Before they got quantized, the Lie algebra was this. Okay, this was known as the DeWitt algebra. And I hope Sajid has shown you. So I haven't really prepared how to derive the Virasoro algebra with the central elements, but if you guys want, I can do this in the next lecture, okay? So it's now going to have a central extension because you see it's the, okay, we'll talk about how it comes about, but it's going to be d by 12, where d is the dimension of space-time, meaning the number of x's. And then we have m cubed minus m and the delta of m plus n. So what does delta m plus n mean? This means that the way I would write it is this, that when m plus n is 0, that's when this is 1. So this whole algebra with the central term, with this term, this is called the anomaly term. This is known as the Virasoro algebra. Okay. And this is the Lie algebra. So the Lie algebra of n infinite dimensional Lie group. Okay. So I'm sure you've seen or at least heard of Lie groups. But in particle physics, we deal with Lie groups which are finite dimensional. But here we see a Virasoro algebra is the Lie algebra of a group which is infinite. And in quantum, right, so in string theory and in 2 dimensions, there's a lot of infinite dimensional Lie algebras play a very, very important role. Okay, So, so to recap, okay, no, so these are very important stuff. So let me just copy them and bring them down here. We will keep those. So these are the L0 constraints. Now, it turns out that for the other ones where m is not 0, we can only do this. If we want to do this as well as do this, then that leads to a contradiction from the with the Virasoro Lie algebra. To see this, if I take if I take the left-hand side, if I take m and n to be m to a minus n or n to a minus m, and this is acting on some on some state, then of course the left-hand side vanishes, right? The left-hand side vanishes, and then what happens is that when this thing does not vanish, right? Because m is equals to n, so this becomes 1. So this term does not vanish, but over here, this becomes L0, right? And this is a non-zero constant. But the constant for L0 is fixed. It does not depend on m. But the central extension, this will depend on m. So therefore, if I impose both of these conditions, I get a contradiction. So the best we can do is to just impose these guys. Okay. So this is very similar to, is somewhat similar to what we do in electromagnetism. Okay. So, and so in the end, these are the conditions that we are imposing. Now, Sajid may have mentioned that the consistent value of A is 1, and the consistent value of D is 26. So if I do this, then I can write down the mass formula for the open string, which is going to be 1 over alpha prime summation from n going to 1 to infinity, alpha minus n dot an minus 1. And the mass operator, so this is for open string. And for a closed string, it's going to be 2 by alpha prime sum goes from 1 to infinity, alpha minus n, alpha n plus alpha minus n tilde, alpha n tilde minus 2, right? And this is for the closed string. Okay. So now the thing is that we saw that L naught plus L naught, this generates time translation, right? Because this is basically the Hamiltonian. You can easily show that L naught minus L naught bar generates the space translations, meaning that this is the momentum operator. Okay. So now, because no point on a closed string is special, we must have translation invariance on closed string. So that means that L naught minus L naught bar acting on phi must be 0. Okay. So that means that if I go back to, so this is to the expansion for this, what it means is that this mode and this operator must be the same. So if I introduce n to be, n goes from 1 to infinity, alpha of minus n dot alpha of n, and n bar is equal to n goes from 1 to infinity, alpha minus n tilde dot alpha n tilde, then this relationship tells us that n will have to be equal to n bar. And this is known as so meaning that the number of, for the closed strings, the number of modes that we excite on the left must be equal to the number of modes we excite on the right. Otherwise, we will not have translation invariance. Okay, so this is known as the level matching condition. Okay. All right, so I'm just going to take a 2-minute break. And while I take a short break, I would like you to think about questions that you.
Yeah, sure. Okay.
All right, so I'm back. Are there any questions? Are there anything that you want me to repeat? Maybe explain? Yes, please.
No, I think it's going fine up till now.
All right. Okay, awesome. All right, so let's, I just want to make sure I haven't really skipped anything important that I wanted to mention. So we have kind of made the jump to quantum strings. Right. So what I want to do today is that I want to go back and, right copy of the expression we had for the mode expansion for the string. Okay, let me just write this again from scratch. Anyway, I have a bit of a confusion about a small factor, so I'm just going to check that. Okay. Things are okay. No, I did not make a mistake. All right. So often we'll use coordinates such as z and z bar. And what z and z bar are roughly speaking, it's something like this. Okay. So instead of, so, you know, this is like, so these are essentially left moving and right moving coordinates. And these are the holomorphic, anti-holomorphic version of this. Okay, so, and all of these, so this is very common in string theory because the left mover and the right mover, they decouple, and also because in terms of holomorphic and anti-holomorphic coordinates, you know, they also decouple, so it's easy, very common to write this. Okay, let me just go back to what I wrote. And this is the worldsheet. Now I'm just using ZZ bar. And so this is the target space coordinate, and it'll have a center of mass. It'll have center of mass terms. And then it'll have terms coming from the momentum center, the momentum mode, the zero modes. Okay. Because as Sajid was saying, when you solve the equation of motion, you're allowed to have a term which is linear in time, but you're not allowed to have a term which is linear in space, because if you did, then your boundary condition would not be periodic. So this, and then we have plus alpha prime by 2 square root of 2. Okay. And then we have terms which are oscillator terms. Okay. So now what we want to say is that we want to take my space-time, which is some 26-dimensional Minkowski space, and replace it by a 25-dimensional Minkowski space times a circle, right? So we are going to consider a small circle. And the motivation of this comes from Kaluza-Klein theory. So Kaluza-Klein theory, and the problem is that string theory is 26-dimensional, and as Sajid says, you know, string theory has a lot of junk. So one of the projects of string theory has been to convert that junk into gold, kind of by some sort of alchemy. So how do you get rid of dimensions in physics? Well, you do Kaluza-Klein theory, where one of the dimensions is very small, so small that you can't see it with your bare eyes. And Einstein liked Kaluza-Klein theory because he, along with I think Klein, believed that if you have a 5-dimensional space-time and you take its 5-dimensional metric So this is a 5-dimensional metric of space-time. You can write it as a 4-dimensional metric, and then a 4-dimensional vector potential, right, which acts like electromagnetism. But then one also has a scalar called a dilaton. So the Einstein-Hilbert action for this in 5-dimension, if you assume your space-time is 4-dimensional Minkowski space times this, gives you a 4-dimensional gravitational action, plus a 4-dimensional electromagnetism, but coupled with a scalar, which is called a dilaton. Now, but the thing is, depending on how you write your action, this dilaton couples the electromagnetism, or it couples this. So you don't actually quite get the the unification that you wanted between gravity and electromagnetism, and because of this pesky dilaton. So that project failed. So string theory kind of wanted to revive that project and basically see that if that could be done so that we can now ignore one of the dimensions or make it small so that we don't see it. And that led to a lot of interesting discoveries. And the point here is that if your space-time is like this, then all these functions can be expanded as a Fourier series in the S1 condition. So all these functions will be periodic in the S1 coordinate, right? So, and then when you quantize it, what will happen is that their momentum is going to be, there's going to be an infinite tower of momentum. But there'll be the low-lying momentum for which their mass will be 0. And so but what is the scale? What is the distance between these energies or momenta? Well, they'll be proportional inverse of the radius of the extra direction. So if the direction is small enough, the energy difference will be very large. So that for low energy physics, you just have to take the 0 mass condition. I think there's a question. Yeah, it's
Yes.
like a cylinder. Yeah, it's like a cylinder, but it's a more general cylinder. Yeah. So so essentially, the low energy effective theory will only have, massless fields, which are these things. Okay. So there are more like higher and more massive degrees of freedom, but if the interaction energy is small enough, if the interaction energy is much smaller than the typical inverse radius, then in whatever units, then essentially you will be guaranteed to have consistent physics, right? So we want to do that in string theory, but in string theory there is a bit of an issue, and the issue is that, well, strings are extended objects. So whereas if you do a quantum field theory here, your excitations are point particles, and the momentum of these point particles in the compact direction will be quantized, right? So we know that we cannot write the momentum operator in a box, but we can write the momentum eigenfunction on a compact direction is going to be periodic, and it's going to be quantized, right? So, but here, so I'm just drawing the wave function, but here, in addition to the quantization of the momentum, we'll also have strings wrapping in the extra direction. And those strings, you can think of them as rubber bands. They will be stretched, and when they're stretched, they will carry some energy. And therefore, the physics that comes out of compactifying an extra dimension in string theory is a lot more rich and nuanced than what we did in Kaluza-Klein theory. Okay, and we're going to see that. So let's assume that our x25 direction is compact, is a circle with radius r, right? So now, on the world sheet of the closed string, we can take sigma, we can do a translation by 2 pi, and on the world sheet, we will come back to the same point, same physical point, right? Now, if I this one's good. Yeah, I knew I'd made a mistake. Mm. Mm. Oh. Yes. This is tau, but this is sigma. Right? And why is that? Right. So right. Just kind of, going back because when we did the mode expansion, it was this form. And what Sajid showed you, and there was no explicit sigma dependence, no linear term in sigma, right?
Mm.
So it was of this form. And we just, right. And what we did was that there was a periodic boundary condition in sigma. So there was cosine of n sigma, but of course it's not linear. Okay. But the string, this condition the string solution had a left moving and a right moving part, right? So because it's a wave equation, second order wave equation. And we know that second order wave equation without any source terms have this beautiful property where the left moving and the right moving parts decouple. Right. So because this thing was the solution of this equation, right? And therefore, this is the most general solution to this equation, right? But this is also, if I write it in terms of T and sigma, this is the solution. But we can also write the solution in terms of sigma plus and sigma minus. Okay. So when we write the solution in terms of sigma plus and sigma minus, obviously we cannot have tau, because tau is not sigma plus or sigma minus. So a little thought shows that the right movers is we basically take half of this guy to the right mover, and we take this guy and also divide it up, but we have to divide it up in a way such that we have sigma minus here. And then we have I alpha prime by 2 square root. And that's because I forgot to write the alpha prime, I2 alpha prime here. There's a square root. So, and then we have the modes, which is alpha n mu divided by n. And now we have E minus 2in sigma minus. Okay. So this is the condition. This is the solution if I write this in terms of sigma minus. And of course, when we write this as now sigma plus, sorry, the left mover, which is going to be function of sigma plus, will be analogous. But now instead of sigma minus here, we're going to have sigma plus. Right? And over here, instead of having, so we'll have a tilde, because these are the left movers. I often get left and right movers confused. And here we'll get E minus 2in sigma plus. Sorry for the squeezing that is happening. Let me make some room. All right, so this is the sigma. Let me write it. Minus 2in sigma plus. All right. So now, if you want to write this guy, what we do is that we add these two things. When we add these two things, we see that this thing in conjunction with this thing, what happens is that the time part remains, gives us this, and the other part is just, gives us the cosine, and tau comes from, because the sigma, the spatial part cancels out. Okay. So what we are doing here is basically did I write that? Yeah. So what we're doing here is essentially, we have broken up these two parts, And mm, yeah, right. So we are basically you know, essentially this thing, and this thing will give us the x right, and this thing, and this thing, and this thing will give us x left. Okay, and just make sure that um, uh, yeah. So right. And so for the sigma for this to be actually independent of sigma, on the non-compact space, what happens is that on a non-compact space, this thing is constrained to be this thing, and that is constrained to be this thing, the momentum. Okay. And because of this, we are left with something where there is no where there are no sigma dependence. Okay. But on a non-compact space, in the non-compact direction, you know, there is really no interpretation, like the momentum doesn't really make sense in the non-compact direction. So in the non-compact direction, these two things don't have to be the same. Okay. So this is something in a, so so I don't know if probably Sajid did not cover that. But one way of thinking about it is that when you did solve for the left and the right mover, to solve from the left mover and the right mover, in principle, one didn't have to put these constants to be the same. Okay. And it's only when we wanted to interpret the sum of these things to have a, which is, you know, if I add these two things, if I wanted the sum of this thing to have a center of mass and a momentum of the center of mass, that's when I have to set x mu and x mu tilde to be equal, as well as P mu and P mu tilde to be equal. Okay. Or in other words, these two things to be equal to P mu. Okay. So I don't know, did Sajid cover this part?
Uh, Well, I would like maybe one of the participants to answer this.
Yeah.
Fatma, can you comment on this? Like,
Rehab is saying that I don't remember that, right? So that's a very good. Um,
no,
yeah.
but I want to hear from one more.
Yeah, please.
I think
Yes,
he did talk about this, but maybe he didn't talk about it in too much detail, so people don't remember.
Yeah. So I mean, that's the thing about string theory is that these things are not hard. It's just a lot of details. There's a lot of details. Okay, so right.
I believe that there has been some overlap, and I'm happy because, of course, it's a difficult topic for someone studying it for the first time. So I'm happy
Right.
that you also covered these things, and
No, it's just that the subtleties in my case they matter, right? The fact that in principle I can choose a different constant here and a different constant here, and I don't have to put these equal to each other. And that has to come from the fact that, when we put these two things together, on a non-compact space, in addition to whatever vibrational degrees of freedom we have, I mean, the string is an object, right? It's an object moving, it's an extended object moving in non-compact space. So it is going to have some center of mass coordinate, right? And it is going to have some, some momentum of that center of mass. All right. So I think that so I want to motivate it from there that although in principle, these constants can be chosen to be different, when we think of the string as moving in a non-compact space, which is an extended object moving, we want to have a center of mass and a momentum of the center of mass, and that's why we have to put those equal. Okay.
right. So I think we can. What do you suggest? We end here because
Oh,
it's already over 5
yeah.
minutes.
Yeah, to be honest, I have gotten to probably half of what I want to cover. Maybe let me see if this is a natural point or if there is. I think this is a natural point. I'll start again tomorrow from this formula. And maybe motivate it a little bit better, and then we'll see how this formula leads to the how it leads to the appearance of D-branes. Okay.
I think that's it sounds nice. So okay, let's so tomorrow you have got 2 lectures and
Yeah.
one is in the sort of afternoon and
Right.
all
So I
right.
wanted
So
to can I ask you a kind of an organizational question?
yes, please.
What is the structure? I mean, how did you reach out? I want to know a little bit about the participants. How did you reach out to recruit the participants of the school?
Well, we just designed a poster and
Okay.
we circulated it. So I guess most of the participants are from Rawalpindi and Islamabad.
Okay.
And participants can correct me if I'm wrong, but that's my understanding.
All right, cool. Anyway, I'll try to get as much as possible, and I think it's important to understand deep brains properly, because that kind of
Yes.
lays the foundation of non-perturbative aspects of string theory, rather than going and understanding everything about advanced string theory. So that's why
Yeah,
I'm going a little bit slowly, as that, these subtleties are very important. You don't really understand the deep brains unless, okay, all right, cool. Okay, Imran, can you also maybe send me a copy of the poster, if you don't mind?
yeah,
All
definitely,
right.
definitely.
Okay. All right. So I'll see you guys tomorrow. I think, when is our first lecture tomorrow? It's 12, right?
Yeah, 12 p.m. Pakistan time.
12 p.m. That's going to be, I think, 1 p.m. Bangladesh time. Yeah. Okay.
All right. So
All right.
thank
Okay.
you
Thank
once
you.
again.
And see you guys tomorrow. Yeah. Thank you. Yeah.